Now by this point in the unit, we've talked about heat, the transfer of thermal energy, a lot. But there's a few special things we want to really hit home, and additionally a few other things we want to add to this topic. First, let's briefly remind ourselves what we know about heat, this transfer of thermal energy between a couple of objects. Now let's pretend we have a couple boxes here, and these boxes each have gas particles moving inside. The box on the left is at 700 Kelvin, the boxes on the right is at 300 Kelvin. So from we know about temperature, which is basically a measurement of the average kinetic energy of the particles, that the box on the left at 700 Kelvin is going to have particles moving way faster than the box on the right. And let's say this is at t equals 0, they're insulated from each other, but now let's say at t equals 1 second, we kind of make that barrier between the two a little bit more permeable so that molecules on either side can affect the other. And when that happens, faster moving particles in the 700 Kelvin box will hit particles in the 300 Kelvin box and cause them to speed up, and in the same time cause themselves to slow down. And as time goes on, the particles in the left-hand box are going to move slower, the average is going to go down, and the temperature is going to be decreased. As we can see in about a minute later, it's 500 Kelvin. And the box on the right is going to have particles steadily speeding up, and it's going to go up to, we'll say, 350 Kelvin. Now let's say another minute passes, and we have now reached thermal equilibrium, the point when the two boxes have the same temperature, so each box contains a gas with particles that have the same average kinetic energy. Now, it's just a reminder to ourselves, not all of the energy is going to go from left to right. Some of the particles over on the right-hand side will speed up, and they might hit some slower particles moving on the left, and that will cause some energy to go the other way. But overwhelmingly, the kinetic energy goes from the left to the right. But we want to notice something here, which is that although they reach the same final temperature at thermal equilibrium, these two boxes didn't necessarily have the same change in temperature. And why is that? Well, we didn't say anything about these particles. They could be different masses, they could be different amounts of gas, and so that could really affect this. So we can't say that for sure, that they're going to change by the same amount of temperature, because temperature is just a measurement of the average. However, we do know for a fact that the final temperature does have to be the same between the two in order for thermal equilibrium to be reached. The other thing we want to note is that closer to the beginning of this process, way more of a drop in temperature is occurring for the left box and way more of a gain in temperature is occurring for the right box. And that's because the rate of temperature change is actually proportional to the difference in the two temperatures. In other words, when they're 400 Kelvin apart, there's a lot of change in temperature very rapidly. But as they get closer and closer to the same temperature, this rate decreases. As we can see, this is not a linear decrease and a linear increase. It is actually an exponential decrease and exponential increase. And this is actually something known as Newton's law of cooling, just saying that as time goes on, the rate of which this is happening decreases as the temperatures come closer to equilibrium. And now that we've looked at these boxes with regards to temperature, let's also make sure we focus on energy. As we mentioned just a minute ago, at the beginning, overwhelmingly the amount of kinetic energy, or internal energy for the entire box, is moving from left to right, but there's still a little bit of kinetic energy flowing the other way. However, overwhelmingly we would say the heat goes from left to right because that's where the net transfer is. The reason why this other path is occurring is because, remember, all of these particles, these boxes, they are going at a variety of speeds. And it's very possible that a faster moving one here will in fact hit a slower one moving here and cause there to be a shift in energy the other way. As time goes on, we can see that the left, from left to right, decreases and right to left increases until eventually we reach thermal equilibrium where Q, or heat, equals 0 because the net transfer is equal in both directions. Now, while the temperatures at the end had to be the same, but the change in temperature didn't have to be the same, energy is kind of the flip. Because we know from conservation of energy that whatever energy was in this left-hand box that has now been removed must have gone to the right-hand box if they're insulated from the environment. So we can look at these and say, well, the internal energy of these two boxes has to be the same throughout. So whatever is lost from the left-hand box is given to the right-hand box. However, we don't have to end up with the same exact amount of thermal energy in each box, because once again, that depends on like the number of particles and things of that nature. Now, what is new about heat that we have not already discussed? And that is the modes of which this heat transfer can have, of this thermal energy transfer. In other words, how exactly does the heat get from one place, or the thermal energy get from one place to another? And there are three main mechanisms of this. The first one is known as conduction. The thermal energy is conducted from one place to another. And this is the transfer of thermal energy directly through a physical material. And we'll look at a little visualization of that in a second. But this literally travels from one part of the material to another. And it requires physical contact. We must have two things touching to conduct thermal energy from one object to another. They must be physically in touch. Now, typically speaking, solids are better conductors than liquids, which are better conductors than gases, and that's largely because of the spacing of the molecules. Solids are very closely packed together, so a change in thermal energy of solid particles quickly affects solid particles close by, whereas liquids are a little more spread out. That doesn't happen quite in the same way, and gases are way more spread out, so it's actually pretty hard to conduct heat through a gas in this way. Additionally, just as a note, typically speaking, good electrical conductors are also good thermal conductors. So in other words, things like metals, fantastic thermal conductors. This is why, for instance, you do not want to, for instance, be stirring a pot of soup or something with a metal spoon, leave it in the pot, and then come back and touch it, because a lot of that thermal energy has been conducted up through the spoon, and you're very likely to burn yourself when you hold on to it, because it transfers very easily to your hand. However, things like wood or plastic, so if you had, for instance, a wood or a plastic spoon, this would not conduct the heat nearly as well. So those are poor thermal conductors. So let's really briefly look at what exactly conduction is like at the particle level. So let's say here we have some sort of rod. This could be like a metal bar or a wooden cylinder, who knows what it is. But we hold one end close to a fire, and as we can see at T equals 0, the particles nearest the fire start to move around a little bit more as they gain more of this thermal energy. Well, when they move around, they bump into the particles next to them and cause them to shift around. So as time increases, they start to move faster, and the particles next to them are moving fast as well. Not quite as fast as those on the left, but they're steadily getting there. And as time goes on, the particles here are bumping around a lot, really hitting these, but even these are bumping around some, bumping into the ones next to them, etc. So this heat is literally being transferred from one end of this solid object to another. But what's important here, though, is that while thermal energy specifically, or kinetic energy of the particles, is being transferred from one end of the material to the other, the particles are not being transferred. The particles basically stay in the same place. It's just by moving around, they bump into their neighbors and give them energy, which causes them to move around more, bump into their neighbors, give them energy, etc. But they pretty much stay in the exact same location. Well, how quickly is heat conducted through a solid object? Well, it depends on a variety of factors. First off, it depends on what type of material we have. So if you have something like metal, it's going to conduct heat way more quickly than if you have something like wood, because metal is a much better thermal conductor. And we'll talk more about how we know that in a second. But it also depends on the dimensions of the object. It depends on the length of the object, so how far apart are the 2 points we're considering, but also depends on the cross-sectional area, how thick the object is that heat is traveling through. Additionally, it depends on the difference in the temperature of the 2 points we're looking at. For instance, as we mentioned a second ago, if that difference in temperature is quite big, there is a lot of heat traveling pretty quickly. But if that difference in temperature gets lower, that is reduced. So this is the equation that we have for the rate of what we call conductive heat transfer, how quickly heat is conducted through a solid object. Now let's talk about all the different pieces here, because there's quite a lot going on. On the left-hand side, unfortunately, there's not really a good symbol for rate of heat being transferred, but we know that Q is a transfer of thermal energy, and delta T is over time, so this is a rate that this thermal energy is being moved. So this is the rate of heat transfer, Q over delta T, and the units would be joules per second, but we know that a joule per second is a watt. So we could say that the rate of conductive heat transfer has units of watts, capital W. And let's talk about all the factors. First off, we have right here K. Little k, that's a lowercase k, it stands for the thermal conductivity of the particular material you are using. And basically this is saying how well does this specific material conduct heat. If you have something that's a good conductor, like metal for instance, it will have a very high thermal conductivity, causing this rate of conductive heat transfer to go up. If you have a very poor conductor, like let's say wood, it is going to have a very low thermal conductivity, causing the rate of conductive heat transfer to go down. Now, these numbers are found experimentally, much like the coefficient of friction or spring constant, things of that nature. They are things that are just we just test out in labs and then get values in tables and things of that nature. And the units look a little gross. It is watts per meter times Kelvin, which I know is a lot, but really all this constant is doing is taking all of these factors here and getting them in terms of watts. It's basically just a proportionality constant that depends on the particular type of material that we have. Okay, now if we look, so that affects how quickly heat transfers. We have that the length between the two different points we're interested in meters, and if that length is greater, there's going to be less quick heat transferring between the 2 points, which makes sense. If I have 2 points very close together, we can transfer heat very quickly. We move them further apart, it takes more time for the heat to get from point A to point B. Now, I want to be careful here. Notice I said it was the length between points of interest, not necessarily the length of the whole object. For instance, if I have my whole object with point, one end and the other, but I'm only checking the rate of heat transfer between this point and this point, well, I don't want the length of the whole object. I just want the length between the 2 points I'm considering. Additionally, as we already mentioned, if we have a greater difference in temperature, not change in temperature, a greater difference in temperature between the 2 points, that means that that rate of conductive heat transfer is going to go up. If you have a very hot side and very cold side, heat goes very quickly. If they are much closer, it goes much more slowly. The last one is where I see people make the most mistakes, which is with cross-sectional area. Basically, how thick is the object that heat is going through. If it is thicker, heat actually flows more easily, and that may trip you up. You might think, well, wait a second, how does that make any sense? Because doesn't it have, you have to have way more heat to go between. But what you have to remember is when you're heating one end of an object and the other, this rate of conductive heat transfer is really telling me amount of heat per unit time. If I have a thick rod, it is way easier to get a larger amount of heat flowing between the 2 points in a certain amount of time. If I heat up one end and one end entirely, I have way more heat being transferred between them per second than I would if I have a much thinner rod. So it is really much more to do with the amount of heat flowing through than it is with how quickly the heat is flowing through. So the second mode of thermal energy transfer, heat transfer, is known as convection. And more than likely you're familiar with this term either from like convection oven or convection currents. Now, how this works is rather than having particles transfer energy to each other, in very poor conductors, so this is often like particularly poor conducting fluids, which are often many liquids and gases, it is way more efficient to transfer thermal energy literally by just moving the fluid around. Rather than having particles run into each other and directly transfer their thermal energy like you do in conduction, in a lot of fluids it is way easier just to get the fluid with a lot more thermal energy to a different place. That is a much more efficient process. And typically this happens by result of density changes. So for instance, if I am heating up this, pot of water, the water right here directly above the flame gets warmer. And when it gets warmer, it expands, it gets less dense, and it therefore rises. And while that occurs, the water that is cooler on top sweeps in and takes its place because it is now denser. And as it gets hotter, it also gets less dense and rises. And then it cools down, gets more dense, and sweeps back in. And you form these loops called convection currents. This is where you get the adage, hot air rises, cold air sinks. Many of you have probably heard that at some point in time, just kind of as like a quick thing to remember. It's not 100% true. It doesn't happen exactly like that for all air or water systems, but it happens a good deal of the time. The third and final mode of heat transfer that we're going to talk about is radiation. Now, I want to be real clear. We're going to talk about radiation and electromagnetic radiation, otherwise known as light, way more next semester. We're just going to touch on the very, very, very surface level right now to understand what exactly is happening here. We're going to talk about it way more down the line. So radiation is the transfer of thermal energy through the emission of electromagnetic radiation. In other words, if you have any object that has really any sort of temperature at all, it is going to be transmitting some of the energy away as radiation. Now, that's not going to be happening necessarily a great deal. Hotter objects transmit and radiate a lot more energy away than objects that are cooler. And notably, though, this is the only way we can transmit thermal energy through a vacuum. Conduction requires solid objects, or at least things to be in touch with each other. Convection requires motion of fluids, like gases and liquids. But radiation is allowed to go through the vacuum of space because it is light. And this is why, for instance, we get heat from our sun. That is the radiation from the sun. Now, like I said, all objects emit this sort of radiation, but it's in different forms and a lot in different amounts. For instance, let's look at a few different scenarios here. Now, we're going to learn way more about what is known as the electromagnetic spectrum next semester, which is essentially the spectrum of light waves. It goes from radio to microwaves, infrared waves, visible light waves, ultraviolet waves, X-rays, and gamma rays. And if we look, this side of the spectrum is lower temperature and lower energy. And this side of the spectrum is higher temperature and higher energy. Now, what I mean by higher energy is not only that this light contains more energy, but additionally, the higher temperature that you have, way more energy is radiated away. In fact, the amount of energy that is radiated away, so this is not for conduction, but instead of for radiation, the rate is actually proportional to temperature to the fourth power. So if you have a very low temperature compared to a high temperature, there's an exponential difference in the amount of energy being radiated away. So let's look at a couple of these real fast. Now, you're probably all somewhat familiar with, for instance, our sun, which is at 6,000 Kelvin, and it actually peaks in the visible spectrum and actually emits a lot of visible light, UV light, and a bunch of other types of light, but primarily visible light because it is at that temperature. Now, if we go a little lower in temperature, for instance, to let's say a little piece of metal or steel that's been heated up, like we see on this blacksmith anvil, that's 1400 Kelvin, still quite hot, and the peak is still invisible, but it's not quite the same amount as the sun. And if we cool this down, for instance, it's going to get more of a red, which is going to be a little bit lower temperature, and eventually we're not going to get any visible light from it emitted at all, because it's going to be too cool. It could still be quite warm, could still be warm to the touch, but it's too cool to emit visible light. Because if we cool down a bit, we start getting into infrared radiation. This is where basically like our body temperatures would be, for instance. So our body temperature is around 310 Kelvin, roughly speaking. And at that temperature range, you are emitting infrared radiation, which is why if you have, for instance, night vision infrared goggles, you can see any sort of living organism because you're detecting that emitted infrared radiation that we can't normally observe with our eyes. And if we cool down even more, we can actually start to even see microwaves being emitted. In fact, this is what is called the cosmic microwave background radiation, or CMBR, which we will probably talk about again at some point in time. This is actually a map, but this is showing us how the entire empty space around our planet is actually filled with very, very, very low-level microwaves that correspond to the fact that empty space is at about 2 Kelvin. So what are our takeaways for heat, the transfer of thermal energy? One, we've already talked about this before, but we want to make sure we can explain the process of heat transfer on the microscopic scale, and additionally, how the rate of that heat transfer changes over time. Initially quite big, over time much smaller. We want to be able to distinguish between the three modes of thermal energy transfer: conduction, convection, and radiation. And lastly, we want to be able to calculate the rate of heat transfer by conduction through some particular solid object given some certain set of parameters.